Hello fellow problem solvers! So today we're doing a problem from the 2009 IMO, problem number 3. This is a phenomenal, just look at this problem. It's a beautiful algebra problem. Though it does take a bunch of experience. Literally the only theory you need to know what an arithmetic sequence is. And I suggest you try this problem out for a minimum of an hour and a half. Yes, an hour and a half at the minimum. Ideally 2.5 to 3.5 hours. Not more than 4.5 hours, you wouldn't have that much time at the IMO anyway. And if you'd like to go along with us, put your first preliminary ideas out on paper for the next 30 minutes. And if you just want to chat with me, like what would you do for the first sort of step? What would be your first step here? Pause for 5 minutes, think about that. And for me, when I see a problem like this, it's, okay, so I need to have a sequence strictly increasing. I'm in the positive integers, and I have these two subsequences. I mean, it's kind of a very, very cool problem statement. And, okay, so how do I even begin a problem like this? Like, I've never seen anything like this before, assuming I haven't seen this problem. What do I do? How do I even connect it to? How do I even see, like, what is this condition? And there are two things you can do to solve problems at the beginning. If you don't feel comfortable with them, like if you just don't want to just jump right in and say, let this be a plus n times nd, and this be a b plus n times e, right? If you don't feel comfortable just jumping in and defining what these two arithmetic sequences are, and then from there getting to this being an arithmetic sequence as well, in that case, and that is most people, and that is, I think, the normal way to, like, not the normal way, the normal being the most common, average way that a good math Olympiad will start a problem. So that normal way is one of two things. You can either solve the problem backwards, which is say, okay, say this is an arithmetic sequence. What information do I have about these two sequences? Like, what are they like compared to this one? And the second thing to do, once you get some like hints basically as to what needs to hold true for these two sequences. Because also think about it. If this was an arithmetic sequence, you would get certain things hold for these two sequences. But if the problem statement is true, and we know it's true, then from here, it follows this in arithmetic sequence, which means the things we know, like the things we figured out solving the problem backwards, hold for these two sequences. And maybe those are some preliminary steps we can take to solve our problem. And the second part is, playing around with small cases and seeing if there's any inspiration there that we can get. So now I invite you, if you haven't already, pause for half an hour and solve the problem backwards for 10 minutes and then try to play around with some cases for 30 minutes, okay? So I hope you paused and did that. So let's first just solve the problem backwards, and let's say the sequence Sn is going to equal n times d plus some constant c. Right, this is an arithmetic sequence. Now what is SSN? Well, SSN is going to, a social security number, is going to be equal to Sn times d plus c, and this is going to equal by this. It's going to equal nd plus c times d plus c, which is nd squared plus c times d plus 1. Yeah, this is SSN then. Okay, and SSN plus 1 will be equal to Sn plus 1 times d plus c, which is going to equal, we're going to get here, literally nd plus c plus 1. So this is going to be, again, nd squared plus c times d plus 1, and we had a plus 1 plus ad. Okay, so what do you see from this, right? From this here? Like, just playing around with these small cases, what do you notice immediately? And for me, the thing I notice is, okay, these two sequences, SSN, SSN plus 1, they have the same coefficient, right? This is not like the problem statement doesn't tell us this is true, but it seems like it has to be true. So maybe that's the thing for us to prove that these sequences have the same difference. Okay? And that's pretty much it at this point. Like, it seems like the difference between these two sequences is D, because that's the difference between these. Like, these are two consecutive members of this sequence, and that's about it I think you can get from solving the problem backwards. And the coefficient maybe here needs to be a square with these two sequences. Maybe that's used in some way, shape, or form. And yeah, I think that's pretty much it. That's pretty much all that I can see immediately that I could use in the problem. Now, pause for 20-30 minutes and play around, and that's what we're going to do now. So, I've written down some things. Now I've put S1 is 2, S2 is 5, S3 is 7. Why did I make the sequence non-arithmetic? Well, I've already gotten everything I can from making it arithmetic. So let me see what goes wrong. Like, that's my play here. Like, what is going to go wrong if the sequence isn't arithmetic? So what happens in this case? And mind you, just by virtue of setting these three elements, these two sequences should not be able to be arithmetic sequences, right? Because if the problem statement is true, mind you, I've only set up these elements. And I've already broken the problem. I mean, it's kind of wild if you think about it like that, but yeah, I've already broken the problem. Just by doing that. Just by doing that. Now, we could say let this difference here be D, difference here let it be E, and then look at a problem abstractly. But if that's too difficult for you, and it is certainly for me, and it was at the beginning, let's set up some more numbers and let's see what they give us. So let's say put S5, and I'm going to use a different color just to see like the different assumptions we're making. So let's say S5, it needs to be greater than 7. It needs to be greater than 9 actually, because S4 is at least 8. So S5, let's make it, I'm making differences are 3. What happens when we make S5 equals 10? Okay, so here I have a 10, and now the difference here is a plus 5 difference. Okay, so plus 5, which gives me S7 immediately. It gives me S7 is going to be 10 plus 5, which is 15. Okay, I have SS4 is going to be 20, SS5 is going to be 25, and I have some of these numbers. Okay, so I have some numbers. Now, what about this thing right here, S6? Well, S6 we know is between 15 and 10. Now, what could it be? So, we've mentioned before, like that in our sort of exploration, we've figured out that we need to have that we will have these differences have the same difference. So, what can we do to sort of test that out? Well, let's see what happens in the converse. Let's see when they don't have the same difference. So, let's say the difference here is 6. And then S6 is equal to 7 plus 6, which is 13. And let's say S6 is equal to 13. Okay, so then we have S8 is going to be equal to 19. So far, so good. And then S4 plus 1, we don't know what that is. But we can say we know SS5 is equal to, well, S10. I already have that from before. So S10 is equal to 25, S8 is 19, And then I have, okay, wait a second. Here I'll have SS4 plus 1 is also going to equal to 25, right? Because this is plus 6. So SS4 plus 1 is equal to S10. So S4 plus 1 must be equal to 10. In other words, S4 must be equal to 9. Okay? And then what do we have here? We have SS5 plus 1, which is S11. And S11 is going to equal 31. And then we have SS6, and this is going to equal S13, and it's going to equal to 30. Is there a problem with this? Pause for 2 minutes and figure it out? And the answer is, well, yeah, there's a problem. The problem is, this is S13, this is S11, but S11 is bigger than S13, a contradiction to our sequence being strictly increasing. Mind you, this is the only condition we have for the sequence. It better be important in some way, shape, or form, and it seems it is right here. We're getting a contradiction with this. Now, do you have enough motivation to try to prove that these two sequences have the same difference in a general case? Here we're getting that this element here on this side is actually bigger than this one over here that's meant to be bigger. Now, how can you sort of formalize that thinking? Pause for 10 minutes and try to do that. And the answer is, well, let's make it so, let's say this sequence is SSN is equal to A plus ND, and say SSN plus 1 is equal to B plus N times E. Now, what is sort of the thing we're saying? We're saying that what we have is this number here, this subscript, is bigger than this subscript, right? And it should generally be bigger. So we're saying that SS6 is generally bigger than SS5 plus 1. Or in other words, we're saying that we're trying to claim that SSN plus 1 is going to be less than or equal to SSN plus 1. But is this true? Pause for 2 minutes to figure that out. And the answer is, well, mind you, the sequence is increasing. So this number is less than or equal to this number. SSN plus 1 is less than or equal to this number. And so S of that number is less than or equal to S of that number. And this is something like generally you can do with sequences that are increasing. Like if you have a sequence or a function, like a sequence is a function from, like this is a function from the integer, from the positive integers to the positive integers. So if you have a function that's increasing, say S is increasing, then you know S of S is also increasing, right? And then you can say stuff like S of A is less than S of B. And from here you can, I think, even infer that S of B is greater than S of A. Just from the fact that S is increasing, you can get the convolutions of F also increasing, or of S here. So that's how we have this thing, which we know is true. And the other thing also follows directly. This is less than greater than or equal to Sn. Now what do we have from here? Well, this thing right here is equivalent to, let me clear this up. So this is equivalent to SSN. This is A plus ND, less than or equal to B plus N times E, less than or equal to A plus N plus 1 times E. Okay, we have these inequalities that need to hold true. Okay, let's subtract A plus ND from all sides. Then we have 0, less than or equal to B minus A plus N times E minus D, less than or equal to A plus D. Actually, less than or equal to D. Now, what do you notice in here? Pause for 2 minutes, figure that out, and the answer is, well, mind you, if E wasn't equal to D, what would we have? Well, then this would be a linear in N. Now, what's the thing about linear functions? they know no bounds. And on one interval, from n0 to positive infinity, it's without bound. Or in more layman's terms, which I like more, is to say, if this wasn't 0, if this was negative, we could set n to be bigger than the absolute value of b minus a, and then this whole value would be negative. Like this would be much bigger than this, and it would get it to the negative, right? If this was positive, well, then we could set n to be the absolute value of n to be bigger than the absolute value of b minus a plus d, or maybe the absolute value of both of them. And from there on, we would have that this would be bigger than d, right? For some n. For n big enough, this would be bigger than d, and that would be a contradiction. So from here, it follows that d and e are equal. In other words, these two sequences have the same difference. And it's important to write stuff down like this. Mind you, this took us like 10-15 minutes of playing around and figuring out like what to do, different cases, and solving the problem backwards. And from that basic principle, we got something. This is worth a point. Like almost without a doubt, it's worth a point. And a point can mean something, and that's why it's important to try out even these difficult problems, see if you can, grab a point or two. Okay, now let's get back to this problem. So let's clear up these faulty assumptions. Okay, so now that we've cleared up the faulty assumptions, then we know that just by setting up a difference of 5 here, that means we're going to have a difference of 5 here. So S6 then is 12. S8 is going to be equal to 17. And we're going to have S of 5, yes, S of 5 is 10. S11 is going to be, so this is plus 5, 22 plus 5, 27. Okay. So now what do you notice in this problem? Is there anything interesting that you notice about this sequence? Where is there a breaking point in any place? Like we need to show that just by setting this up, we're breaking it. Okay, we've set up a 5 now. Why are we breaking? So let's see, what do we have? We have S2, S1, S3, S4, S5. We're missing S4 is a question mark. S6 we got S6 is 12. S8 is going to equal 17. And we have S10 and S11. S10 is equal to 25. S11 is equal to 27. Now what do we do here? Well, let's think about the differences between, like, we're looking to show that the difference between any two successive members is the same. So let's look at what these differences are. Okay, now here there are 3. Okay, now here there are 2. There are going to be 2 here, like with every single one of these, right? These are the indices here differ by 1, and the difference here is a difference of 2. However, like we have between S3 and S5, we have a 7, we have a 10. So S4 is going to be of a distance 1 from S7 or a distance 1 from S5. Right? So it's because S4 can be either 8 or 9. If S4 was equal to 8, we'd have a contradiction because this is 17, this is 20. Right? S8. And if we got a 9, then we would have a contradiction here. This would be S10. S10, these two things aren't equal. So it seems if there's a difference of 2, we're sort of, maybe the issue is here that we're having a difference of 2. I mean, I've set up S5 equals 10. Maybe we need to try out a different number, say. So we have all these different values now, and let's see what does this mean. So we have a difference of, so again, differences again, we have a difference of 2 here. Between these two, S4 is going to be of a distance, 3 is in the middle. So, it's a difference between these two, it's not super bad. And the difference between these two is of 6. That's a big jump. So this distance is also of 6, but there's a thing in between. But these are two numbers which are consecutive, which have a difference of 6. These two numbers have, so what is the average distance? Like, we're looking at distances between, so it makes sense to look at the average distances. And here we have S13 minus S8 is going to be 37 minus 23, which is equal to 14. And how many differences are there here? Well, there are 5 differences. And you can think of this as S13 minus S8. And the reason there are 5 differences is you'll have S13 minus S12, and then plus S12 minus S11, plus S11 minus S10, all the way till S8. Now, those are the differences, and there's 14 over 5 is the average, so to speak, difference. Now, what does that mean? Pause for 5 minutes, think about that. Well, the answer is there's going to be one that's bigger or equal to and less than or equal to 14 over 5. And namely, that means there's going to be a difference that's at least 3, and a difference that is at most 2. So it's like, okay, like we're getting another distance of 2, another distance of 3, right? Let's see what else we could get. Here's where I invite you actually to go ahead and pause for the next 15 minutes and try to play around a bit with these averages, distances, and let's see what you get for it here. Why would you get a contradiction? If you would, like you must, how would you get it? Pause now, and here's the next step. So the big idea here is, mind you, we had, like, how do we get this distance here? Right, there was a S13 and S8. Like, why were they interesting? Well, we got a 13 here, and S8 we got from the 7 here, from S3. And here we had a chasm of 6. Like, here the distance between these two is always like a constant between these two and these two, so on and so forth, a distance of 6. So we had a big chasm, and of the S's, S5 and S3, and then that produced 2 more intimately linked, closer than these were on average, right? So a big distance gave us a small one. And then if we look at SS15 and SS14 plus 1, and why we look at those? Well, because these also have a big chasm, but the indices, 14 and 15, are closer than the 5 and the 3. So again, this is a bigger chasm of 6 now, and that gives us even closer, tightly coupled together distances later on. An average distance of 1, which means that S39, S40, S41, S41, S42, S43, all the way till S45 are all consecutive, right? So this gives us those numbers are then tighter together, and because they're 1, then we can sort of finish up the problem from there in all likelihood. But there's this thing that's happening between numbers which are closer together, like indices, like SIs, which are close together, produce SIs which are far apart. Now, if this thing is unstable, whatever that means, if it goes, it can't go as small as possible, and can it go as big as possible? Like, pause for 5 minutes, think about that. Can it go as big as possible? And the answer is, well, it really, really can't, because mind you, if, say, the difference between two SI was, say, bigger than, if here the distance was D, if the difference between two SI was bigger than D, what would happen? Right, you had SSN, and then the next one was SSN plus 2D, right? That was a bigger chasm. Well, what you would have is this would be like some t, and this would be t plus d. Okay? How many numbers do you have in between this? In between these two indices? Well, you have, 2d minus 1 or 2d. So you have 2d numbers, or 2d minus 1, roughly 2d numbers, but d minus 1 available numbers. And that's a contradiction, which also means this distance between two successive SIs is bounded from both directions. So it can't get as big as you want it to get. It's pretty much bounded by, in this case, an 8, and it can't get as small as you want it to get. The question is can it get as small as you want it to get? So now it makes sense to maybe look at what happens when you have a smaller SI, like a small distance between the two of them, and what happens when you have a big distance between some two. This is what you can do with averages, and here I invite you, we're going to now, this is enough playing for me. If you'd like to play around some more, try out some other sequences for 30 minutes, try to push the problem further. But now I'm going to try to see and play around more abstractly with these differences, distances between any two successive ones of these, and see if that leads to anywhere interesting. So now let's clear up the board and do that. Okay, so the board's been cleared up, and I want to point out another thing here that I'm doing. I've written down everything we figured out so far, this and this. And mind you, these two things together, maybe some partial progress is what we're trying to do now. Like this intuition, big and small distances. Write those things down if you figure them out on a test, because these can be partial points. This, I believe, in my humble opinion, this would be worth 2 points, having this. And maybe having some progress, some progress who is bigger and smaller, looking at these averages, almost definitely gives you 2 points. Almost definitely. Now here, if you haven't paused and played around a bit yourself for 20 minutes, then please do that. But now let's continue together. So what do we have here? Okay, so let's take some small distances. Let's see what happens when, say, some s of some n plus 1 minus Sn is equal to some m, which is the smallest distance possible. Right? Okay, so what did we look at then? Well, we looked at what happens with ss of n plus 1 and ss of n plus 1. Okay? So what was this equal to? Well, this was equal to, what do we have? N times d plus a. So it's n times d plus b, n times d plus b. And this is equal to n plus 1 times d plus a. Okay. Now, the average distance between these two is going to be ssn plus 1 minus ssn plus 1 over their difference, the difference between these two, which is m minus 1. This is the average distance, and that average is going to be this minus this, which is equal to, so d minus b minus a, right? This is bigger than this. I want to have a mental representation that this is smaller than d. Okay, so this is the average. And what does it mean that it is the average? Well, it means there's one that's bigger than the average and one smaller than the average. Right. So there's a difference here that's bigger than or equal to or less than or equal than the average. And what we're saying here is that the average will produce a bigger distance, right? Like if we have a small one here, we'll produce a bigger one later on. Now, how big can this be? Well, the answer is, well, this average needs to be less than or equal to, let's say that the biggest one of these is equal to some, for some m, Sn plus 1 minus Sm is going to, well, max, or I don't want to use lowercase b, let's use e. let's say this is the biggest one, the biggest difference possible, well then E is going to be greater than or equal to this. Okay? So this is the average distance. And actually this over f minus 1, my bad. So now we have some relationship here. And then we're saying also that when we do this thing, when we have these two numbers, when we have s of m plus 1 and s of m plus 1, that these two numbers, like what are they equal to? md plus b, like md plus b and m plus 1 d plus a. In other words, their difference is again equal to the same thing. And so the average here is ss of m plus 1 minus ss of m plus 1, actually the opposite. Now it's the opposite. And over how many are there between them? Well, there are e minus 1 between them. And this thing is equal to the same thing we had here, like d minus b minus a over e minus 1. And now what are we saying? We're saying that this produces a smaller one, right? In general. And this smaller one needs to be greater than or equal to m, right? M is the smallest one. And now what do we have from here? Like, is this something that we can use? Does this lead to a contradiction? Anything? And the answer is, well, I might choose to pause for 5 minutes and see that. And the answer is, well, yeah, it leads to something interesting. From this one, we have that e times m minus 1 is greater or equal to d minus b minus a. Like when you have the same thing on both sides, you equalize, see what happens with this inequality. And this is greater than or equal to m times e minus 1. Okay, so far so good. Does this always hold true? Well, em gets cancelled, we get a minus e here, minus m here, move m here, and from here we get that m is greater than or equal to e. Okay, but what was m and what was e? Well, m was the smallest one, e was the biggest one, so by definition, e is greater than or equal to m. And now m is greater than or equal to e, which means m and e are the same, i.e. the smallest difference and the biggest difference are in fact the same. And this finishes up the problem. And this is actually one way of solving the problem. You're sort of trying to go ahead and formalize this intuition that you had, that when you have a small difference between the indices, and you can figure this out through play, like that's the best thing you can do. If you have a small difference, you'll get a big one later on, right? And if you have a big difference, that means that later on you'll get a small one. And you're trying to see, like, wait, this can't go on forever. This can't grow forever. And that's how you can end it. Another way we could have also come to this is to say, so we have this for some m, and now we're going to have some, so we're going to have a difference that is either bigger than or equal, or like greater than or equal to this, or less than or equal to that. And to be precise, like we could also have said this. Take the small difference, right? Sn plus 1 minus Sn, this is the small one. So Sn plus 1 minus Sn, in other words, S of Sn plus 1 minus S of n plus 1. We here get that there is a difference that is going to be greater than or equal to this thing over here. Like from here, we're going to get a big difference, namely a difference greater than or equal to this thing over this. Or in other words, we're going to get a difference of, let's even do a weaker estimate, of d over Sn plus 1 minus Sn. So there's going to be a difference here that's greater than or equal to this. So we're going to have some j such that Sj plus 1 minus Sj is greater than or equal to this. And now we have this big difference, Sj plus 1 minus Sj. And from there, what can we get? Well, from Ssj plus 1 minus Ssj plus 1, or even just Ssj, both work. From Ssj, here we're going to get a difference between these two. We're going to get a small difference. And this small difference, or a big one, like a distance that is going to be about this size. Right, so we're going to get some, and we're going to get a small difference, which is going to say this, for some SL plus 1 minus SL. Now what happens when you combine these two things? Well, actually a smaller difference means this. So what happens when you combine this? Well, what happens is you get this situation right here. Sj plus 1 Sj, you get this. Now, mind you, if I switch these around, I can write this as j plus 1 j, n plus 1 n. And now this is the same as this, but this was the smallest difference. And now this is a smaller than or equal to difference. Like when this was the smallest one, we have a smaller one. I mean, all of these are then equal. And then we have equality holding true for every single one of these. In other words, when you get a small distance, we're looking at the smallest distance, then we're going to get all distances which are the square root of d. This gives us the square for this difference between difference for these arithmetic sequences. And from there, from this equality, you could also just go ahead and say, we could finish from here as well. Like that's another place we could have finished. We could have then said, okay, we have equality all the way around. And we were looking at Ss n plus 1 minus Ss n, all the differences here. And two of the differences here are, the first difference mainly is Ss of n plus 1 minus Ss of n. And this thing is constant throughout, because this is the difference between these two members of a sequence is a constant. And here we'd get that this is equal to the square root of d. And from there we'd finish up. Because if it's a constant here, then this constant is equal to the square root of d. And we'd finish up nicely because now we know if this is the smallest one, the square root of d, that means that we have now b minus a is equal to the square root of d. The square root of d is the smallest one. I mean, let's actually call this, now let's make this a d squared, this equal to d. The smallest one is equal to d. Now say there is two members which are bigger than d, like whose difference is Sn minus Sn plus 1 minus Sn is bigger than d. Then what would we do? Well, the same sort of logic would apply. Like we could also do it through here, but another way to go about doing this is then this is at least d plus 1. And from there we'd have the difference between Ss n plus 1 and Ss n plus 1. We'd know this difference on one hand would be equal to d squared plus a minus b, and which would be equal to d squared minus d on one hand, but on the other one, how many things are here? Well, there are at least d consecutive members, and there are at least d differences here. Given d is the smallest one, then this is greater than or equal to d times d, which is d squared, and a contradiction, d squared minus d and d squared. And that would finish up the problem like that. So there's like the two ways to finish up the problem, although as well, we could have just gone ahead and taken then the similar thing with the maximum one. Now, this is a problem that I really like because of the problem statement. And if you just look at the problem statement just like that, it's beautiful. And when you read it in your first go, I think you don't really notice how important, how crucial the condition that this is, number one, an increasing sequence, strictly increasing one, and secondly, one of positive integers, right? Because we're using fact that the smallest difference between two positive integers is one, and there's the smallest positive integer. So in any subset of positive integers, there's going to be a smallest one and a smallest difference, and sometimes the biggest one as well. And I just love it because of that and the aesthetic, just how it looks. This finishes up this lovely, beautiful problem. I hope you had fun with this. And as always, thanks for problem solving.